In this section, we're going to talk about titration. Titration probably is one of the most exciting experience for you guys in the Chem 1 lab because just one tiny drop of the solution from the burette can change the color of the reaction, and depending upon the color of this solution in aluminium flask will give you something to brag about towards your coworker or even against your instructor, because I usually be challenged by my students when I supervise Chem 1 class for the titrations. So this is pretty good experience. Well, in the Chem 2 class, here when we conduct an acid and base titration, remember for the acid and base, the pH is going to change. So the change of pH is something that we're going to discuss here in this lecture. So speaking of types of titrations, we can have a strong acid titrated with a strong base, or strong base titrated by the strong acid. So here I'd like to clarify, okay, so which one is the analyte, which one is the titrant. So the one here in the burette is what we call the titrant, and the one here in the beaker is what we call the analyte. Okay. So if we have a strong acid titrated with strong base, so for this particular example, so strong acid will be here. And for the titrant would be the strong base. And of course, we can switch the solution so that we can have a strong base titrated with a strong acid. So this is a type of titration that we're going to discuss. And another type of this titration we're going to discuss here is either the weak acid titrated with a strong base or the weak base titrated by the strong acid. And at the end of this discussion, we're going to talk about the polyprotic acid, or the mixture of the acid titrated with a strong base. So there's 5 titrations that we're going to discuss. First, let's look at the titration curve if we have a strong acid, strong base for the titration. So here, the strong acid is going to be titrated by the strong base. How do we know it? Because if you look at the bottom here, so that is the strong base is added through the burette. And this is the titration curve. From this titration curve, it's obvious we can find there are 3 regions. Region A, B, and C. And the region of A is what we call acid region. What is acid region? Because pH is low. Remember, the lower the pH, the stronger the acid it is. So this is the pH that's starting off very low. So for example, the pH starts with 1, so that's very low in pH. Why pH is start off very low here? That is because we got a strong acid, right? Strong acid leads 100% dissociation, so we got a lot of hydronium in the solution. So that's why pH starts off low, and pH keeps low as we add strong base, because there's still going to be excess amount of hydronium, and so that is where the pH is most likely is going to be. So this is what will happen for the region of A. But what is even more important is region B. So region B is right here. So in the region B, we start to see pH rises dramatically. This is where we start to see the solution of the analyte in a beaker or in an aluminium flask, starting from pH is roughly 3 all the way up to pH to 11. we're talking about the pH change of 8 units. That is usually what happens if we have a titration between strong acid and strong base. But sometimes the change of pH units by 6 is also can be considered as this type of titration as well. So there's a huge change of the pH unit by only 1 drop of the strong base solution. So here I'd like to give you an idea just what is like if we have a solution have this pH unit that jumped by 6 to 8 units. In this case, we'll talk about the concentration of hydronium here because it's pH, right? So the concentration of hydronium here in the aluminum flask has been decreased by the factor of 1,000,000 here or 100 million. So that is a dramatic change of the concentration of hydronium only caused by that a tiny little drop of an NaOH in the solution. Halfway of the jump is what we call the equivalence point. Equivalence point, according to the name, so that means they have the equal amount of something. So that is the equal amount of strong acid and strong base in theory, mathematically. And when we look at this equivalence point, we find out that is roughly somewhere around 7. Why 7? Why pH 7 for this equivalence point here? So we need the explanation for that. Remember, for the strong acid and strong base reactions, for example, HCl react with NaOH. So you may recognize the products are water and NaCl, right? So water is a neutral compound. So what is the acidity property of this salt NaCl? Is that neutral or acidic or basic? So this is something that we need to determine before we can explain why the equivalence point has a pH that's roughly 7. So when we look at, in this example, sodium chloride as a product of this titration, sodium comes from a strong base. Chloride comes from a strong acid. So such salt is, you got it, SASB, strong acid, strong base. The pH for this kind of salt, neutral. So that is why, as we can see, pH here is roughly equal to 7. So the salt as a product of this titration can actually indicate what the pH range we are looking for the equivalence point of this titration. For example, in this case, strong acid, strong base, the salt is made by these two, and it's neutral, so equivalence point must be somewhere around 7. As we pass the region of B, so we have the region of C. Region C is where we have excess of a strong base like sodium chloride. And of course, it has a very high pH as sodium chloride, sodium hydroxide, strong base, 100% dissociation. So we have a high concentration of hydroxide to speak of. So pH is high and stay high. And for this titration, we can use the indicator to show just how the color is going to change. And of course, one of the good indicator that we can use for this titration, phenolphthalein. So once we have phenolphthalein, remember the change is from colorless to pink. Right in the middle of this range of changing color is what we call endpoint. So for the endpoint, it's a pink color. It cannot be red. Okay. Once it becomes red, so that means it's going to be go over all the way up as far as we know. So there has to be the pink, and that pink is what we call endpoint. Endpoint is a pH 1 indicator starts changing color. And of course, endpoint must be in the region of B in that jump, in the change of pH dramatically. Well, a good design would be the endpoint and the equivalence point are the very same, but in practice, it's not always the case. Okay, but one thing for sure, both points here, equivalence point and end point, must be on the region B. Must be in the region B, because one tiny drops of this titrant can change the pH dramatically, and also covers a range of indicator to change color. So this is basically the features of a strong acid, strong base titration, or we said strong acid titrated by the strong base. First, pH start off low, going slow, going up slow. And when we see the big jump, so that's usually we experience the pH jump from 6 to 8 units. So that's what happened between strong acid and strong base, caused by, of course, only one drop of a titrate. And as of the equivalence point, the middle of this jump is where the moles of strong acid and strong base becomes equal to each other mathematically. And pH for this equivalence point should be 7, because the product as a salt is made by strong acid and strong base. So from the discussion we had in chapter 16, the pH for such salt is neutral, equals to 7. And above the region B is what we have, region C, so that's a strong base, because we got excess of strong base. And here we have the end point, which is where, or the pH, where the indicator changes color. But we must make sure that the end point is within the region B. It can be lower than the equivalence point or slightly higher than lower than the equivalence point, but nevertheless, it has to be the region B, and only in the region B. So this is the features of the titration between strong acid and strong base. In our case, strong acid titrated by the strong base. Well, the second titration curve I'd like to talk about still comes from strong acid and strong base, but this time it is a strong base titrated by the strong acid, as you can see, HCl added. When we look at this titration curve right here, we realize it's just like a vertical flip of the titration curve from the previous one, because remember the previous one is like this, right? So if we flip vertically, so this is the titration curve we have now. And from the previous discussion, we realized that there are 3 regions. We got the region A, B, and C. Region A, because we start off with excess of strong base, so we got a lot of hydroxide. So concentration of hydroxide is high, so pH start off high, and it going down slowly. And when we talk about the region of B here, now this time pH drops dramatically. By how much? By 6 to 8 units. This is where the solutions start from basic to acidic by only 1 drop of strong acid. Halfway of this drop lies in equivalence point, where the moles of strong acid and strong base mathematically equals to each other. And like we discussed, the pH of this equivalence point must be roughly equal to 7, because the product here is a salt from strong acid, strong base, so pH is equal to 7 because it's neutral. As for region of C, there's going to be excess titrant. Titrant here is HCl, so pH is going to start low and it's going low slowly. So what is our choice of indicator here? Can we still use the indicator like phenolphthalein? Okay. Imagine you have a titration. Remember, because there's a base in the flask, since it's a base, it shows pink color or red. As we add HCl from the pure red to it, the color gets fainter, 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 and should go to colorless. From red to colorless, sometimes people may not be that kind of sensitive to pick up that colorless. People probably always think about it, there's going to be a faint pink, may requires a little bit more HCl or strong acid from the pure red. That screws up the entire experiment because a little bit more HCl, we talk about the volume right here, which is not the volume we are looking for. Remember, titration is a technique that has the great precision as well as accuracy. So the indicator that changes color from red to colorless is not going to be a very good choice for us to use as an indicator. So what we're going to use here is something else. So for example, if it is yellow in the base, but it turned out red in acidic. So basically, we're looking for something from yellow to orange. And that color change is so intense, and we can pick up the sudden change of the color, and then it will give us the end point clearly that is lie in the region B. Once it's a region B, our end point serves the point to indicate the end of the titration. So choose an indicator sometimes can be very tricky. Okay, so even for a strong acid strong base reaction, phenolphthalein is good for one, but it's not going to be good for the other. So this is something that I want you guys to realize and to keep that in mind. Our next titration is the titration of a weak acid by the strong base. How do we know it's a weak acid? Because we do not dissociate weak acid in the net ionic equation, as you know. So OH minus is strong base. So this is basically what the titration curve of this weak acid titrated by the strong base look like. And again, it has 3 regions, but it also has one spot. We call it D. It would be much easier for us to discuss if we can superimpose the titration curve of strong acid and strong base together. While the strong acid with the underscore indicates strong acid is what is in the aluminum flask as an analyte. Once we have these two titration curves superimposed to each other, now we start to see something that we can discuss. First, the point of D. The point of D is the pH of a weak solution weak acid solution before the titration. And of course, we definitely see the higher pH. Why the higher pH? Because we talk about a weak acid. Weak acid does not have 100% dissociation. So less amount of hydronium, the higher the pH. However, it is the region of A that is interesting. Remember, we got a weak acid, HA. So if we have a weak acid that has been reacted by the strong base, and according to the reaction right here, as HA disappeared, we have a more of A minus. HA, A minus, is something we call conjugates. HA is a weak acid, means A minus is a weak base. Remember in the section that we discussed before, if we have a coexistence of weak acid and weak base as a pair of conjugates, the solution is what we call buffer solution. All right, so that is why for the region A, we call it a buffer zone. Right in the middle of this buffer zone here, which is halfway of this equivalence point, halfway of the equivalence point, that means exactly half of HA is reacted to form A minus. Half of HA, another half is being converted to A minus, so that means the concentration of acid and its conjugate base are the very same or equal to each other. Remember, it's a buffer solution. We can use the HH equation. If we use the HH equation, CB over CA, if they both have the same concentration, that would be log of 1. Log of 1 equals to 0. So the pH of this solution at this point right here is actually pKa. So from this region A, halfway to this equivalence point is where the pKa lies in. So how do we know this halfway? So say once we finish the titration, we find out, okay, so the titration, so equivalence point is 40 milliliters. So we take a half value of 40. So we just raise up a line at 20 milliliters to hit titration curve. The pH of this curve, this point right here, is what the pKa is. So that is why if we have a weak acid be titrated by the strong base, once we finish titration curve, we can go back and find out where the pKa is. So this is one extremely useful piece of information we can get from this titration curve, especially for weak acid. Region B here, again, we start to see the pH increase. Here, I'm not going to say dramatically because it's not going to be that much, okay, compared to strong acid and strong base one. Again, this still, we can see the pH from acidic to basic caused by only 1 drop of this strong base solution. So usually pH jump is between 1 to 6 units, depending on just how weak this weak acid is. If it's very weak, pH jump is only caused by 1 unit. If this weak acid is relatively strong, so sometimes we can get to up to 6 units of pH jumping. Just like the pH curve we discussed from previous, halfway to this jump here lies in the equivalence point, and the equivalence point is where we see the equal amount, equal moles of acid and the base. And of course, if we look at this pH of this equivalence point, it's somewhere around here. So I would like to read that pH is roughly equals to 9. Remember, pH equal 9 is a basic. Okay? Why this point is basic? As you realize, the salt is made of weak acid and strong base. Weak acid and strong base, it is a base that's got left over. Base got left over, the salt is basic. Since the salt is basic, we got the equivalence point that's greater than 7. So there's additional information we can get from this titration curve. And region C is where the strong base is. And of course, it's going to follow the discussion that we had from that, okay, from previous discussion. So pH is going to be high, and it gets higher slowly. All right, now let's talk about a weak base is being titrated by a strong acid. Okay, so this is how the titration curve look like. Again, just like the weak acid and strong base one, it has 3 regions and 1 spot, spot D. Just like we vertically flip the previous one vertically. And if we can superimpose the strong acid and strong base curve, and we start to see we can have a lot to discuss about. First, the point D. The initial constant, so the pH of this weak base solution. And it starts off low. That is because partial dissociation of a weak base. So we do not have enough amount of hydroxide like a strong base to keep pH higher. So we start off pH low for the weak base. Just like the previous one, the region A is what we call the buffer zone. Why? Because according to the reaction here, weak base is going to be reactive with strong acid so that we can have a salt or whatever that is. But here, as we can see, we have one more proton difference between HB plus and the B. So we now understand this is a pair of conjugates. Weak base is to a weak acid. So we got a pair of conjugate weak acid and weak base. So that's a buffer solution during titration. So that is why, again, we call the region A as a buffer zone. And of course, right at the middle, we call it halfway to the equivalence point here. This is where the concentration of this pair of conjugates are equal to each other. So once they're equal to each other, according to HH equation, pH equals to pKa. pKa of what? pKa of its conjugate base. No, I'm sorry, conjugate acid. So HB plus. So how are we going to get a pKb from the pKa of the conjugate acid? Remember, pKa plus pKb for a pair of conjugates is equal to pKw, which is a 14.00. So pKb of the base is equal to 14 minus pKa of its conjugate acid. So we cannot get a pKb directly from titration. We have to get pKa of the conjugate acid of such a base. Then we can get a pKb out of it by subtracting the pKa from 14. Region B, again, we see the pH start falling quite a bit. Okay, this is where we start to see the pH start from basic, so 8, all the way down to the low pH because we're adding strong acid, right? And halfway to this dropping, we have the equivalence point. This is, of course, again, this is where the moles of a base equal to the moles of strong acid. And the pH of such equivalence point, as you see, that's about 5, is less than 7. Because the product, the salt, made of strong acid and weak base, we got a little bit more acidity left. So such salt is acidic. So determines the equivalence point of the solution at equivalence point, acidic. As for region C here, because we got a more strong acid in the solution, so pH is going to stay low and going down slowly. The last titration curve I'd like to talk about is a diprotic acid titrated by the strong base. Why this particular topic? Because this titration has profound application, especially in biology. Because I'd like to remind you for amino acids, most of them are diprotic acids. And some of them are even triprotic acid. Okay. So that means there's two places where we can see the protons. So for example, we see the protons right here. And also we see one of the protons right here as a source, okay, of our acid. So we got two protons in this amino acid we call aniline. And when we look at the titration curve of this diprotic acid titrated by the strong base, obviously we can see two well-defined equivalence point and well-defined titration curve superimposed to each other. So for example, we see a very good titration curve right here. So here all the way up here, so that is our first titration curve. And of course, if you can see second titration curve, that is from here on. So this is our second titration curve. And for our first titration curve, that's highlighted in yellow. So from yellow line down. So we got the two titration curves superimposed on each other. And so here we have a two equivalence point indicating two protons in such acid. For the first one, point C here, is where this acid start have this proton lost. And of course, when we look at this region, we have a region point of A. So this is where the pH of the weak acid solution. And halfway of this buffer zone, the first buffer zone here is what we have the peak A1 of this diprotic acid. And this is the equivalence point. For the equivalence point, we understand it's going to be acidic because weak acid strong, so the weak acid, right? But this is the first, so that's why it's going to be slightly acidic. For second one, it's going to be basic. And for this curve right here is the second buffer zone. For second buffer zone here, halfway of this buffer zone lies in the pKa2. So from this titration curve, we can actually figure out what the Ka1, Ka2 easily. And of course, the same titration curve could have a different interpretation when we get into the biochemistry class. Because for a biochemistry class, they are looking at titration curve. They're looking for titration curve in this way, in this region. So the one I labeled as red, okay, not yellow or black, because those yellow region and black region is what we look for in chemistry. And that is it for this topic. and for titration curve. Okay, so I would like to highlight what we have discussed as a summary. So for strong acid, strong base, depending on which one as an analyte, if we have strong acid as the analyte staying in the beaker or the aluminum flask, so pH is going to be low, start off low, going up low, and we have a huge jump of pH in the region B. Halfway out this jump is the equivalence point, and the pH of this equivalence point must be somewhere close to 7. And once we have an excess amount of base, because of strong base, so pH is going to be high and stay high. So that is for the strong acid titrated by the strong base. And if we turn this around, as I say, strong base titrated by the strong acid, so we just simply flip this titration curve vertically so that we have region A start off high in pH and steep decrease in pH for 1 drop of acid. And of course, we got the region C, which is a strong acid. And of course, we can either monitor the pH or we can use indicator to show whether we should stop the titration. For the indicator, remember, the indicator we choose for the changing color must be in the region B, the jump of pH. It cannot go anywhere close to region A or C because this is where the solution is still going to be quite away from the equivalence point, so indicator wouldn't be accurate enough if we choose such in our experiment. All right, so another type of titration is weak acid titrated by the strong base. And of course, 3 regions with 1 spot. Okay, so 1 spot, that means for the weak acid, pH start off higher because it's weak acid, not 100%, not as many of hydronium to begin with. And region A here has a special meaning. It's a buffer zone. Okay, and if we have a strong base titrating the weak acid, so we have pH drop in the pH rising. And if you have a pH raise, so we need to know where we find equivalence point and what the pH of the such equivalence point is going to be. And for the other titration curve, so the weak acid titrated by, so the weak base titrated by strong acid. So again, buffer zone. Okay, so halfway to the equivalence point of this buffer zone here is the pKa of the conjugated acid of this weak base. So how do we get the pKb? Remember, pKa plus pKb equals to 14. So this is how we get the pKb out of it. For diprotic acid titrated by strong base, remember we got 2 titration curve superimposed on each other. Not only did we see 2 well-defined equivalence point there, we also should be able to get the pKa1, pKa2 from these 2 buffer zones of titration curve. All right, this is it for our second topic of this chapter. And later on, in the third topic of the chapter, we're going to talk about slightly soluble salt. And that should be it for this section, and I'll see you guys later.